Hey everyone, Triple NI here, and I know I've not uploaded for a really long time. It always is. Oops, it always is that way. Whenever I'm in the midst of something that troubles me a lot, and so I thought I'd just give you a quick midsummer update because I am 5 weeks into my summer vacation and I've got 4 more to go. Okay, so well, maybe it's not exactly the middle, but this is everything that I've been doing so far, and if you watched my previous video on the peril of power electronics, you'll know what I've been doing, and that flopped. So if you remember, I showed you version 4, and the bad news is it flopped, and it flopped badly. So I decided to give up on version 4. I've given up on version 4, and for a period of exactly 1 day I had no idea what I'd be using to charge my capacitors. I considered an interleaved boost converter of sorts, but I didn't, because a few weeks back I happened to find this on the 4HV forums. I printed this out. Well, search for this title on Google and you'll find the paper, and frankly this is an excellent design. Excellent in the sense that it's simple and it kind of works. So I don't think any explanation is needed. So anyway, I took a few ideas from this. It's supposed to be a continuous mode flyback converter, so yeah, I've decided to go continuous mode. But things didn't exactly turn out that way, as I'll show you now. And the design I came up with was this. So I have a 10 ohm current sensing resistor on the secondary side connected to the negative pin of the capacitor, not to the secondary winding, because if you connect it to the secondary winding, from the secondary winding to ground, then you get a negative voltage which I can't measure. This creates another problem. I'll tell you about that later. So the the current waveform on the capacitor feeds to this gate driver, which has a low threshold. So the output goes high while the secondary discharge is in progress, for a short while at least, and that resets my 555 oscillator. So I got off with using very simple parts. It's a lot simpler than my original design, and that's good actually. The simpler the better. So this is the gate driver, this is the secondary resistor, smoothing capacitor, and a few assorted discretes. Very few parts, honestly. Not like version 4 where I had to have a dedicated comparator and voltage references and all that kind of jazz, as Dave Jones would say. So let me power this up for you. This camera is proving difficult to move. We'll concentrate on the oscilloscope. Yeah, let's hope you can read all the volts and current amps per division. I've got them set up accurately here. So right now my output is short circuited. I've got this yellow jumper wire across the leads of my capacitor, and in normal designs that would just cause a huge current spike in the primary, but not in my case, because I've got feedback from the secondary. So let me turn the power supply on, and of course I have to short these two jumpers. So I short them in 3, 2, 1 and short. So you can see a few waveforms on the screen. Let's go one by one. Let me turn off channel 1 and 2. So this is the primary waveform. As you can see, it's at 4 amps per division. So 1, 2, 3, 4, 20 amps. Ah, crap. Yeah, maybe I'm just measuring this wrong. Let's put it at 10 volts. Sorry, 10x, which is what the probe is, and change the units back to volts. 200 millivolts per division and 500 millivolts per division. Yes, so this is 20 amps on the primary, which is manageable. No saturation, but it could have been a bit better. It's mildly continuous mode. I don't think you can see the current offset over here. Probably just too small. And now I turn on the secondary side current, as you can see, the current drops down. It doesn't go all the way down to 0. The primary starts up again after the secondary. And of course this is smaller than, the peak value is smaller than the peak value of the primary. So it's at 200 milliamps per division. So 1, 2, 3, it's around 700 milliamps on the secondary side. And this is the blanking signal from my gate driver. As you can see, it goes low while the secondary energy transfer is in progress. So once the secondary current reaches the low threshold of the gate driver, it goes high. Well, it goes high because of the NPN transistor, it's inverting. I couldn't find a gate driver with one inverting, one non-inverting, so I had to make do with this. So even though I've short circuited the output, there's no huge current peaks on the primary. So let me turn the thing off, turn it back on, remove the short and charge it again to 200 volts. So you can see the complete charge cycle. And done. That took around 3 seconds. So before I do anything else, I discharge these caps. I'll zoom into the oscilloscope to show you exactly what goes on. I'll go the rest of the way just by shorting it. Done. So now back to the scope. That should be enough. As you can see, the frequency is variable. At the beginning of the cycle it's kind of low because the secondary transfer takes a long time, but the frequency goes up. And I think it's also operating in BCM now for the remaining half of the charging cycle. So that was an ironic thing. I designed for continuous mode and it operates boundary mode. That should tell you a lot. So anyway, I can get my caps charged to 200 volts in 3 seconds. So 30 joules in 3 seconds is around 10 watts of power average. Also, the advantage of this design is I can charge capacitors of basically any size with it, since I have feedback from the secondary. Even short circuiting the output is not going to harm my converter in any way. Let me demonstrate. Short the jumper, then I keep doing this. As you can see, the frequency changes to compensate for the short circuit that's happening on the secondary side. I don't know if you can see that. Yeah, you can see that. Okay, huge sparks there, so let me turn this off. So yeah, that's pretty much it. I'm done. And I'm calling this version of the capacitor charger version 4 block 2, since I'm a huge fan of the Apollo program. Apollo 8 is my favorite mission. So block 2, I've got the perf board cut out for this, and it's actually smaller than the other 2 versions of my capacitor charger, if you can see this. So now that I've got the test bed working, I just have to put all this here and it will be done. And I hope to shoot my railgun for the first time by the end of this month, May 2018, because I've got most of the other systems ready. Capacitor charger, capacitor bank, and my triac bank. Well, I'm using triac since I couldn't find anything else of this size that can handle this current, 6.4 kiloamps. And anyway, triacs work both ways, so you can use it as an SCR. I don't think there'll be any issues. And now to the problem I was talking about. So if you look at this design, oh well, let me put it another way. This is my secondary side. This is, okay, well, this is ground. These are my caps, and this is the 10 ohm current sensing resistor which goes off to the gate driver's input for feedback. If I connect my rails directly across the high voltage terminal of the caps to ground, there's gonna be an obvious problem, through an SCR of course. The current that flows through this cap also has to flow through this 10 ohm resistor, and 2 things can happen. Either this 10 ohm resistor blows up or it severely limits current. So 200 volts by 10 ohms is what? 20 amps maximum, and my railgun is not going to like that. So instead, I've got to put my my rails directly across the terminals of the capacitor, even though the negative side is not grounded. So that creates new problems, and I have no idea how to drive my SCR then, but hopefully problems will take care of themselves. And till then, thank you for watching.